So good morning, everybody. Welcome back. Hope you had a good night after this very intensive first day. So today we are going to proceed with the description of interferometric basis we started yesterday. I will make a summary. I will summarize very briefly in 5 minutes what we said yesterday, just to remind you some notations and some principles. Just maybe one word. It is completely normal that you don't understand all the details of what I'm presenting. You know, it took us many years to understand, and sometimes we discover that there are some points that we did not understand correctly. You know, this is called research. And just relax and try to grab as much as you can from what we say. We intentionally decrease the level of technicity of what we are presenting. And we could use many more formulas saying complex principles. And we try to be as basic as possible so that you can understand what is really important in the lecture. But you understand that having 4 hours of lecture per day is something very intensive, and you cannot assimilate everything at once, okay? You will have a copy of these slides. There are some books. If you need some references, I have references I can give you, not written by myself, but by colleagues. For instance, on this topic on SAR interferometry, there is a fantastic paper, 25 pages, written by Bamler and Hartel, and it is the reference for everybody. Not because these ones were really fun, but they made a summary of what was known on this topic at a given date. Okay, so if you want some insights on what I'm presenting, we can recommend you some literature and some papers. Okay, and yes, as I said, just open your mind, open your brain, and start to feel comfortable with this, with what I'm presenting, independently of your background. You know. So, SAR interferometry basis, what did we see yesterday? We started with the very basic of SAR focusing. We ended up with this very well-known expression when you have a scatterer located at a given location in range and azimuth, okay, which is a coordinate system of a SAR acquisition. You have a response which is proportional to the reflectivity of the scatterer, located at this very coordinate R0, X0, and through a impulse response, which is also called an ambiguity function in all terms of radar, which has generally a sink shape, okay? And the sink is an approximation for a Dirac. A Dirac is a infinite precision response, and the difference between this sink and a Dirac is given by the resolution, the width of this impulse response, which depend on the bandwidth. And the last term is extremely important for us because it is the phase which depends on the distance, and this is how we are going to measure slight variations of the distance from one when you observe the same scatterer from different positions. Okay? I gave some application of this phase spatial diversity, and the big problem of SAR interferometry is to determine the elevation of a scatterer by measuring it with the radar. The radar can only measure, when I make an image of this table, I can only measure the position of my computer along the azimuth axis and in distance, but I don't know if it is here or at another elevation. If we want to do it, we can use spatial diversity. We can use measurements performed from slightly different positions. Okay? I go over all the details we mentioned yesterday to go to this configuration where we have 2 images acquired from slightly different positions, okay? And they are co-registered onto a common geometry. This is essential, okay? You need to co-register the images so that you know that if you have a scatterer which is over your reference geometry, then it will fall exactly at the same position in the 2 images. Okay, so this is if you observe no difference between image 1 and image 2, it means that the scatterer is located here. If you observe a slight variation of the position in one image with respect to the other, this means that the scatterer is not located exactly where you think it is. It is somewhere else. And how to measure this variation of position when it is much smaller than the range resolution cell, the range resolution, and one solution is to use the phase. Because with the phase, you can measure this position with a precision which is given which is proportional to the wavelength. Okay, it's a fraction of a wavelength. This is extremely accurate. Okay, if you take X-band sensor, the wavelength is 3 centimeters, so it means that here your precision is much better than 1 centimeter. Okay, from space. I mean, this device is measure the response of the Earth from 600 kilometers, and you are sensitive to millimeters. Huh? Okay. Finally, this we analyzed. We very briefly described the decomposition of this change of phase between two positions. So I measure from the first sensor, this scatterer in blue here, I have a phase. I measure from the second position. When I make the phase, I compute the phase difference between these two acquisitions. I have a number which I can decompose into two terms. The first term is the phase difference given by my reference geometry. If the scatterer is exactly at the elevation of my reference plane, then the phase difference would be 0. If it is above or below, it will not be 0. And this component, which is called the topographic phase, this is what we want to estimate, has a very simple expression. It is proportional to the elevation, and the coefficient which relates the phase to the elevation is called the kz. Okay, it is called the vertical wave number, although it is not a vertical wave number. But this is how people name this quantity. Okay, kz. Let's call it kz. It depends on the geometry, the distance from the scatterer to the reference plane. This is something you know. The incidence angle from this reference position to the sensor, this is something you know also. The baseline, this is something you use during the design of the acquisition and the wavelength. So all these factors here are known, okay, and they depend on how you design the mission. When you want to perform your own interferometric acquisition, you will have to specify all these factors. Yeah? In general, they are all fixed, but the baseline, so people ask you, which baseline do you want? Okay. And designing a baseline there are some rules, and we will see it later today. There are some rules to choose reasonable values. Okay. And the last thing you need to know about interferometry is this phase wrapping. Okay, the phase, when you compute it, lies over the domain of the real numbers. Okay, but in practice, when you estimate a phase, you estimate it over a unitary circle in the complex domain. Okay, real axis, imaginary axis, and it lies between -pi and +pi. You cannot get outside of this. And when you measure this phase using this operator, this arctangent operator, you transform this phase into this one, but you don't know it because you cannot measure this value. And so when you look at an interferogram, you get something like this. You get fringes. Okay, one fringe corresponds to a change of color. Let's say from blue to red. Okay, this is negative, and this is positive phase, and you go down to negative. Okay. So one cycle represents a value of 2 pi between this point and this point. You have 2 pi, okay? And 2 pi corresponds to what is called the height of ambiguity of your configuration. Yes?
So you have from 0 to 2 pi, but on the graph it's from pi to -pi?
Yes, this is the 2 pi is, you start from, let's say that blue corresponds to this negative value here, and red corresponds to this one.
Oh, yeah, okay.
Okay? So you have 2 pi, and this is, to get 2 pi, you are, 2 pi corresponds to a change in elevation which is given by the ambiguous height, okay? So how fast you would describe this fringe depends on the value of kz you selected, okay? Here you have an illustration. This is with the small baseline. Small baseline, you have a very gentle, slow variations, okay? You have a kind of low pass description of the topography. And with a large baseline, you have much more details, but we feel that in the presence of noise, and all the measurements we are doing are noisy, then it would be difficult to guess if you are to analyze these changes values, okay? So a good combination would be to use both baselines and say this is the first guess of the topography, and then here you have the details. Okay, frequency plays a role, but this is... Yesterday we saw, we we just saw the very basics of phase unwrapping. This is an essential step if you want to reconstruct a digital elevation model, because the wrapped phase cannot be directly converted to topography unless you want to reach this useless result, when you have this sudden variation between the maximum of the ambiguous height to the minimum, etc. So, sorry. To do this, there is a principle. The principle of phase unwrapping is the following. This is the true phase you want to retrieve, okay? And this is the one you measure. And what do they share? They share that they have the same gradient, okay? The phase variation are the same, except that here you have big jumps, okay? And the objective of phase unwrapping is to remove these jumps, okay? And this can be done using some wrapping and derivation. In 2D, you can also use, and this is why interferometry became possible, you can use, okay, so we need to, sorry, in order to unwrap the phase, we need to derivate the wrapped phase, the one we measure. We derivate, we wrap it, and after we integrate the phase back to retrieve the original one, okay? This integration is crucial, as I showed yesterday, if your original phase does not satisfy some sampling condition, which is, for those who know, this is a Nyquist sampling condition. And if the original phase does not satisfy it, and you never know if it really does, okay, during the integration you will have an error, and this error generally propagates, and at the end you get nonsense, okay. And in order to avoid this nonsense, in 2D, you can use a very simple fact that what you want to retrieve, a DEM, is a gradient field, okay. So this is a mathematical property. In practice, what does it mean? It means that when you start from point A to point B, you should have the same height difference independently of the path you follow to go from one point to the other. Here you can go to the right of the mountain directly, if you're a good climber, to the left, etc., etc. Okay. So, and all these paths should give you the same results. And this allows you to detect erroneous points or paths that are likely to be better than others, so you want to avoid errors when you unwrap phases, okay? Today, the solutions that are implemented, like in Snap, you all know Snap, maybe you don't know Snap. Snap is the reference software from ESA to manipulate Sentinel-1 data and other kinds of data. There is a phase unwrapping algorithm inside, which is excellent, okay? It has been developed by the I think this is the Stanford University, and it is the commonly accepted algorithm. Okay, 25 years ago, people were arguing, were comparing phase unwrapping algorithm, and finally we came to the conclusion that this kind of approach here with p equal to 1 gives nice results. Okay, and they provided an efficient implementation in addition. Okay, so the interferometry processing chain is the following. We start with from the acquisition of the data, we co-register the data, and we compute the raw interferogram. Okay, so we get this. We compensate the reference geometry, which in the older time was always a flat terrain. So this is what we call this flattening. We were flattening the face. Okay. Today, as I said yesterday, images are focused on digital elevation models. Why? I will maybe go back in the slides. Why do we focus on digital elevation models? Because we want to avoid this kind of situation where one point is too far away from the reference plane. So if you follow even a very rough guess of the topography, let's say the Copernicus DTM, which is available to everybody, you will be in the Amazonian forest, you will be maybe a little bit over or within the forest, which is perfect. This is where we want to lie, okay? So we use this as a first guess, and this is what biomass does, okay? It focuses on this depth, and after what you find is relative, or you know that you are relative to this reference geometry, okay? So this, okay, so we got a flattened interferogram, we unwrap it using this phase unwrapping algorithm I mentioned before, and after we geocode the result. This geocoding is, normally radar people don't like geocoding because this is 3D geometry, it's something this is better done by cartographers or geographers. I don't know why we don't like it. At least I don't like this too much. It is complex. You need reference point. There is no Fourier transform inside. Okay, and we really love the Fourier transform. Okay. Some examples we saw yesterday. Okay, so today we are going to. Yeah, we didn't speak about this yesterday. Okay, so we are going to give another look at the same thing. Okay, which is even more practical. In practice, you will, unfortunately, never get very clean interferograms as the one I showed before. Okay, which were clean for you, because the world is as it is. It is noisy. Okay, your telephone works in an incredibly noisy environment. We are surrounded by noise, okay? And in this case, we need to implement some signal processing technique that help us cleaning the signals and gaining some insight on the quality of the information we have acquired. So this is just another way of presenting interferometry. We are acquiring an image, okay, which is, after focusing, the image is made of an amplitude here, rho, and a phase, okay? And both of them are normally quite noisy, especially the phase component, the one which corresponds to the distance to the traveling delay between the radar and the object. This is deterministic, okay? But here in the object, I mean, if you measure a forest today, you measure it in 10 minutes, you may have a slightly different response because of wind, because of rain or raindrops which change, whose position change. You will get roughly the same signal, but not exactly the same, okay? And this not exactly the same plays a big role sometimes, okay? So let's talk about speckle. Speckle is why many people who are not specialized in signal processing prefer to use multispectral data rather than SAR ones, because there is this speckle. When you look for the first time at a SAR image, it doesn't look nice, okay? And you need to apply some processing to make it look nicer, okay? So speckle is not a noise. It is modeled as a noise, but it is a physical effect, okay? When I measure this kind of environment, this is a sketch of a tropical forest, I will have responses from every scatterer located inside resolution cell. And the global response will be the sum of all these contributions, weighted by this complex exponential term. At the end, I will get, when I make this sum in the complex plane, I will sum up contributions that are more or less not related one to the other, completely random, okay? The phase changes. We'll see later that the phase is uniform, so it is completely random. And we make this sum, okay? And at the end, we get this blue vector, which corresponds to none of the contributions which were summed up to create the final vector. So in this case, the result appears as very noisy, and this is called the speckle effect. So in SAR, not all the you don't have speckle everywhere. You have speckle over most of the parts of an image, but not everywhere. In some special cases, when you have one big scatterer inside one resolution cell, let's say you are measuring this city, and you have a big building with a metallic balcony, and this will respond with a very strong response, which much larger than the one from the surrounding scatterers. And in this case, we will have what we call a deterministic response, where I will explain later what this is. And we have this situation where we have one scatterer whose response dominates the response of all the others, and the other extreme case is natural environments, where you have within the resolution cell some scatterers which have similar importance, okay? Let's go through the isolated scatterer. When you have one scatterer whose response dominates. These are the maths, okay? I will not comment them, just give you the solution. This is the equation of SAR imaging, and if you replace inside this expression the density of reflectivity with the response of a single point, at the end you get this very simple expression here. You have an amplitude, a phase, and this is the impulse response in azimuth and range. So here you have no speckle, because you had one response, you measured it, and this is what you get at the end, okay? So here the image you have is deterministic. It is made of an amplitude, okay, whose squared value is called the intensity, and this is what you use to estimate the reflectivity of the environment, okay, to measure, I don't know, dielectric properties, roughness, humidity, okay, this is what you will use, and the phase, okay, which depends on many factors. The phase is a function of the position of the object in space and also on this absolute phase factor of the scatterer. On the opposite, if you are looking at distributed environments, distributed means made of a large number of contributions. In this case, you cannot simplify this expression. This reflection coefficient, in fact, is a density of reflectivity, which covers the whole resolution cell. And when you sum all these contributions, you have the random walk I mentioned before in the complex plane, and you have speckle, okay? And the speckle effect, as we'll see on the next slide, is well represented by a Gaussian noise. Okay. Here is another way of looking at what I mentioned before without integrals, without equation, just drawing. Okay? This is what you get when you measure a strong scatterer. When we say a strong scatterer, we don't talk about the size, we talk about the reflectivity. Okay? This one has a very strong reflectivity because it is metallic and it has a trihedral shape. Okay? And when you measure this is a calibration reflector, and it is surrounded by grass. Okay? Let's say you measure the response of this calibrator plus the grass one time, you get this result here. So this is in red, you have the response of the big calibrator alone, and when you sum the responses of the surrounding grass, which has a much smaller amplitude than the one of the scatterer. So at the end, you get almost a response of the big calibrator. You come back 1 month later, you make the acquisition, the same acquisition. The calibrator is still the same. The grass changed because you have the wind or the grass grew up or whatever. And of course, you will have a different response from the grass, but all in all, when you sum all the contribution, the sum is dominated by the one of the calibrator. Okay? So you have almost the same response at 1 month of time interval. Okay? So this is called a coherent scatterer. This is what is used in differential SAR interferometry, for instance. You want to look at scatterers whose response remain stable over time. Okay? So this kind of response is not affected by the speckle effect. Okay? On the opposite, if you do it of a natural environment, such as a forest, you have one realization, you come back later, another one, and they are not related. They are independent completely, okay? Because they correspond to different realizations of the random walk in the complex plane. This is speckle. Okay? It doesn't mean that you need to throw away the measurements. Huh? We'll see later how to use it. A little bit of modeling. If you read the paper by, this was, of course, the modeling of speckle was not done by radar people. It was done by opticians, okay, well before, okay, because they have exactly the same effect with coherent acquisition in optics with lasers, okay. This speckle is well modeled by a product model, okay, which says that your measurement S is the product, can be modeled as a product of a Gaussian complex noise times a term which is interesting to you. Okay? In this term, I have the true intensity of my environment, and I have the mean phase of my environment, the one I will like to use when I perform interferometry. Okay? And so the information you want to retrieve is here. Okay? It's inside your response, but it is affected by a multiplicative noise. Multiplicative noise are strange to handle. Huh? Most of the signal processing you might have done before takes into account additive noise. You have the true value plus noise. In our case, we have multiplicative noise. Okay. This is due to the physics. So this is your acquired signal, which is a complex Gaussian. Okay. It has a zero mean. Okay, perfect, because otherwise we will use SAR to create. I mean, this is not a source of energy. And it has the variance, okay? The variance of my image corresponds to the mean reflectivity I want to, this is what I want to measure when I do SAR focusing. And I don't measure it, okay? one way to look at SAR, when you look at a SAR image, you don't display this complex or real part or imaginary part. Normally, you display the square modulus here, which is called the intensity. It is an estimator of the intensity. Let's have a look at its properties. It is not biased, means that if you make an average of what you have measured many times, you will converge to the true value, which is nice. But here, this is a very annoying problem with this estimator. It has a very, very high dispersion. Okay, you are measuring, in average, the right thing, but with very big oscillations around your mean. Okay, the variance is equal to the squared mean. This is maybe the worst configuration you can have with a positive value. Okay, so this is not good. You need to do something. You need to apply a speckle filter. Okay, and how do we do this? And after I will show you examples. One very simple way to do it is to do multi-looking. Okay, multi-looking. How do you do this? You grab somewhere, and we see what we mean by somewhere. You grab several realizations of your non-multi-looked intensity, and you average them. Okay, this is extremely simple. It is optimal in the normal case. You cannot do better. Okay, in the normal case, and by doing this, you keep this very nice property of no bias. So if you do this, the mean of your estimator will correspond to the true value, which is always something we're looking for. And the variance, compared to what we saw before, has been divided by L. So you are dividing the dispersion by the number of acquisition you use to compute the intensity. So this is excellent. So you need to average as many samples as you like, okay, to reduce the effect of speckle. One example, I represented here the PDFs, I mean the density of the probability density functions, okay, the statistics of this intensity when I use one sample, no filter. When I use two samples in the speckle filter, 8 and 32 samples. Okay, here I indicated with the colors. The color indicates the mean intensity value, which corresponds to all of these distributions. Now, if you look at this one, can we guess from this distribution here which curves correspond to which mean value? It is extremely complex. Okay, so it means that when you have a mean of 8, which corresponds to the sine line, okay, you have this represents the probability to fall in the surrounding of a given position, and you see that your probability is very, very spread, which means that you have a huge dispersion. When you use many samples to apply your speckle filter, your distribution starts to concentrate around the mean values. Okay. In practice, it means that if you look at, I don't know, a rough surface and a smooth one, when you apply a speckle filter, you will start to see the difference. Otherwise, before they were oscillating and you could not discriminate them. One example, this is a detail of a scene I know very well because this is the Oberpfaffenhofen in Germany. Okay, you cannot recognize because this is one detail of the airport runway. This is grass. Okay, grass measured at L bands with and you have different graphs. This is a footpath, and this is graphs, and these are corner reflectors. Okay, calibrators, and you realize this is a speckled image, no filter. Okay, we take the single look complex, squared modulus, and we look at it, and this is the phase, which is really random. Then you believe me that it follows a uniform distribution. If we want to separate the footpath from the grass, if we apply the threshold, you see that we will have a lot of false alarm. Because of speckle, we have oscillation. Okay? When you select, I don't know, one pixel here, and you move to the next one, you can have a black or white color. It changes considerably. Okay? But our eye, which is able to somehow understand averaging, tells us that we have different regions in this image. Okay? We can identify them. But if we had to segment them, this would be difficult. Then you can apply a speckle filter. Okay? You can apply multi-looking using a speckle filter with a very simple procedure. You use what we call a convolutional filter. So you take a box. Okay? This is a boxcar filter. You take a box. For each position of the box, you compute the mean of all the pixels falling into this box. Okay? And the resulting value, you assign this resulting value to the center pixel of the box. Okay. This is the most simple one. Over homogeneous areas, you cannot do better. Okay. And we see here that, of course, now we start to see that it's easier to discriminate this region from the footpath. Now, if I apply a threshold, I will make almost no error if I want to discriminate the two regions. So this is the objective of speckle filter. You see that this speckle filter is not that fantastic when you need to deal with non-homogeneous regions. This is a response of the scatterers here. Calibration scatters, and after smoothing, you have a kind of blurring because this filter is not a clever one; it's the most stupid one. Okay, and it blurs, it spreads all the pulsing because it is made to filter homogeneous region. In homogeneous region, you don't care about resolution. What you want is the right reflectivity. Okay, if you apply it over urban environment, over pond-like scatterers, then you will lose resolution; it will spread. Okay, so there are many techniques that have been developed to counter this effect. The leaf filter is one of them. Okay, it is made on masking, so you see that you gain resolution here. But what do you lose? You lose radiometric accuracy here. If you look at this image and the one before, you see that this one appears as slightly more noisy. Okay, and this is a constant in SAR. When you gain on one side, you lose on the other. There is no magic, okay? But, okay, so this is the leaf filter, which is based on directional masks, okay? Today, if you want to find the state of the art, you need to go on speckle filtering. I would recommend to read papers written by my colleagues in Paris and Telecom Paris. They do incredible techniques using deep learning and using advanced techniques, and they provide you with a speckle filtered map that are incredible. Okay, but the basic behind the physics is just this sliding box. Okay, over forest I use sliding boxes because I don't want to spend so much time filtering speckle. Okay, so how do you deal with speckle with interferometric pairs? Okay. We do exactly the same because it works. Okay, interferometry relies on the fact that the phase, okay, between one acquisition and the other, the object phase, okay, the one which is unknown. What we want to measure is the phase corresponding to the difference of path to R1 minus R2. This is what we want to measure. But if, let's say, the phase of the object changes from one acquisition to the other, there is no way we can say, oh, this is due to the object, this is not due to my geometry, and it will affect my interpretation of the chain of the path. And so the hypothesis of SAR interferometry is that the phase of the object remains constant between two acquisitions. Okay, can just tell you that this is why. For biomass, the revisiting time has been set to 3 days because we knew that there was good reasons to believe that the response of a forest would remain constant or correlated over 3 days at p-band. If you measure the same forest at x-band, there is no way you can remain coherent over such a large temporal lag, okay? Because the stability depends on the wavelength, the movement. Everything in radar is related to the wavelength. The wavelength of p-band at p-band is like this, it's 70 centimeters. So if you have small, slight movements within the forest, they just correspond to a few degrees. If you do the same thing at x-band, then it corresponds to 2 pi. It can lead you to phase variations that are huge. Okay. And we just generalize. You don't need to understand all of this, okay? I'm just explaining. My objective here is to describe this term, okay? But the generalization of the intensity, which was the square modulus when you work with one image, is here called the covariance matrix, okay? Covariance matrix tells you, computes the intensity of the first image, the intensity of the second image, okay? And the cross correlation, one image times the complex conjugate of the other, okay? So you average this, and at the end, you see that this cross correlation can be factorized as a term which is called the normalized correlation coefficient, cross-correlation coefficient. This is what you do in, how you would call it in signal processing. In interferometry, we call it the coherence. Coherence is the most important indicator of the quality of your interferogram. This is what you look at. When you look at an interferogram, you can, looking at the phase without looking at the modulus of the coherence, at the correlation coefficient, is most of the time useless. Okay? You need to have a look at it to understand what's going on in your scene. And you will see later, I will show you how you can provide an interpretation when you are looking at a correlation map. So this tells you how well correlated your acquisitions are. Ideally, if you want to perform interferometry with a very high level of quality, this correlation coefficient should have reached the maximum value in terms of modulus, which is equal to 1. If you have a correlation of 1, it means that all the samples you were using when you computed your covariance matrix were well in phase one with the other. They were all agreeing. So when you look at environment, this means that if you had speckle, you had the same speckle in the first acquisition and in the second acquisition. Okay. In this case, your correlation reaches 1, and you can really trust your interferometric phase. Okay. If the correlation is close to 0, we know from the statistics that the interferometric phase is useless, and you can forget it. Okay. You cannot use it, and you are limited by the physics. Of course, in practice, we never estimate a mean, but we use this multi-looking principle. Okay, so you compute your covariance matrix by using a finite number of samples, and you can, of course, from this we can extract the multi-look expression of the coherence, and this expression is known by every people doing SAR interferometry. When you read a paper, this is even people who don't really understand what SAR interferometry is can provide this formula, because this is how you actually compute your coherence. Okay, it's made of the denominator. The numerator here is a cross correlation between image 1 and image 2, and it is normalized by the square root of the product of the intensities of each image. Okay. A few drawings showing you why this is important. This is here on the left-hand side, you have the distribution, the PDF or histograms as you like, of the phase, okay, as a function of the modulus of the coherence. Okay. When the modulus of the coherence is very high, is close to 1, your phase is tightly distributed around its mean value. Okay. The mean value is 50, okay, and you see that the distribution is very tight. When the coherence goes down to 0.8, 0.6, 0.2, 0.2, you cannot use the phase. You see that the distribution is very wide. Why is it bad? Because with this wide distribution, it means that the probability to get phi 0 or to get phi 0 plus, I don't know, plus pi divided pi plus 90 degrees is almost the same. So you will measure a highly varying phase, okay, because the coherence is not high enough. And this is this lack of correlation most of the time is not due to you, it's due to the environment which change between two acquisitions. Okay? This is a very common reason. Over the Amazonia, for instance, you may have flooding between two acquisition dates, and in this case, the scene changed. Okay? The nice thing, Kostas showed it last week, is that after the flooding, you get coherence back with the first image. Physics are really strange. So this tells you that the quality of the phase depends on the modulus of the coherence. Good. And this tells you, this is shown here. Of course, this is how this changes with the number of samples you use to compute the coherence. Okay? If you just take the interferogram and you don't average it, you make no speckle filter, then this is the relationship you have. Okay? When the coherence, the true coherence is equal to 1, you don't even need to filter. Okay? The phase you measure is the right one. Okay? But when the coherence goes down, let's say to, I don't know, 0.5, you have a standard deviation of more than 60 degrees. 60 degrees is a lot. Okay? If you convert it to 8, you see that you are doing a fantastic error in 8. Okay? So if you want to reduce this dispersion, what you can do is to average. And if you average, if you take only 16 samples, okay, for coherence, let's say your coherence is 0.5. If you don't average, you get 70 degrees of dispersion. If you take only 16 samples, you go down to something like 18 degrees. So you reduce a lot dispersivity. You should average. Okay? You need to apply a speckle filter if you want to understand the interferometric phase. Okay? And the last drawing is important too. It shows you the relationship between the true value of the coherence, okay, and the one you estimate when you apply multi-looking. Okay. So when the true coherence is equal to 1, when your environment doesn't change between two acquisitions, then even if you don't average, okay, you get your estimate will be the correct one. Okay. If the coherence goes down, one may show that the estimate you get with the multi-look approach is biased. You don't measure the exact, you don't measure the true value, okay? This offset can be seen here. If I have a true coherence of 0.2 and I use only 4 samples to compute my coherence, I will have an estimated coherence of 0.4, okay? If I want to get the true value of the coherence, I need to use enough samples. If you don't do it, your interpretation will be wrong. You say, oh yes, my field is well correlated, but you will measure the wrong coherence, okay? So your interpretation on the quality of the phase, here the quality of the phase depends on the true value of the coherence, not the estimated one, okay? So you will have a wrong picture, okay? So let me show you this with a few examples. These are interferograms that were prepared by a long time ago by Kostas Papatanasiou from DLR. I robbed these interferograms from him. This is the absolute phase. This is, sorry, the phase, the absolute one and the wrapped ones from single look without averaging, okay, for different values of coherence. Of course, these are simulated pictures. And when the coherence is equal to 1, you have no speckle. No speckle because the object phase doesn't change from one acquisition to the other. And when the coherence degrades to 0.2, then it's hard to recognize your interferogram. But you may tell me, oh, here I still recognize circles. Yes, because we use specific geometric shapes, okay? And our brain is a very good computer, okay? But if you take a more realistic picture with this is a DTM, digital terrain model, converts it in terms of phase here in an absolute way, and after phase wrapping, okay? And you see that when the coherence degrades and you don't average, it is very hard. Here you cannot recognize the original interferogram, even with the coherence which is I don't know, even at 0.6, if you had to convert this to elevation, you will have such a very noisy DTM. So how does speckle filtering improve your estimation? It improves a lot. Here we took the picture of two well representative cases, a good coherence, true coherence of 0.7, okay? And a bad one of 0.3. 0.3 is considered to be the lower limit. Below 0.3, it's hard to work with an interferogram. Okay? You see that 0.7, when you use 8 looks, you start to have a rather stable phase estimate. 16 looks, you have a very good estimate of the phase. For a true coherence of 0.3, even after 16 looks, you still have a very noisy one, and you should improve. You should use more looks to get a more stable phase image. Here you have the same results computed for a more realistic case, and you see that with 16 looks, 16 independent pixels average to produce, in the case of a coherence of 0.7, we get a rather satisfying estimate of the original phase pattern. Just to tell you that this, you see that when the fringe frequency or when the phase is rather stable, we can realize that the phase estimation is good, but when it changes very fast, you may have small errors that are created by speckle and that we are not able to analyze. Okay? So the speckle filtering comes at the cost of a loss of resolution, and you may, by averaging over large areas, you may blur the original DTM and have problems during the reconstruction. So the conclusion is that speckle filtering can help you, but everything you gain has a cost. Okay? The cost is a loss of resolution, and it is very important to try to perform SAR interferometry in conditions where you have a high true coherence value. Decorrelation. What creates decorrelation? Why do you have a correlation of 0.3 and 0.7 in some cases? There are many, many factors that affect this. I'm going to show you pictures to explain you what's going on, but the most well-known terms of decorrelation are what is called thermal decorrelation. This is due to the presence of noise at the receiver. Geometric one, due to geometry. Volumetric decorrelation, and this is why you're here. If you want to analyze forests, this is what you want to do. We use decorrelation as a way to gain insight of the volume, the structure of the volume of a forest, for instance, and temporal decorrelation and other terms. Okay. One important point is that all these terms here the total coherence is well represented by the product of all these terms. So it means that if somebody fails during the processing of your interferometric images, let's say you have a loss of correlation due to a bad processing. Okay? And after processing, the true correlation is 0.7. Since this is a product and all of these terms have a modulus which is lower or equal to 1, if at one stage you get a very low coherence, the overall coherence will be low. Okay? This is why, if you want to perform SAR interferometry, you need to be excellent. You need to be very, very good at all the processing stages. Thermal decorrelation. This is due to additive noise, which does not come from the scene. It comes from the sensor. It's like for your telephone. And your telephone adds noise to the signal it measures, and this noise affects the coherence of your interferometric acquisition. This is the relationship between the thermal decorrelation and the signal-to-noise ratio. Signal-to-noise ratio is the ratio of the intensity of the reflectivity of the scene divided by the variance of the noise. And you should be, when this ratio is too small, when you're on the left-hand side of the curve here, your correlation falls down to close to 0. And in this case, you cannot retrieve the original coherence, okay, because of this product structure of the overall coherence. I can show you an example. This is the scene. All my example will deal with the scene of Oberpfaffenhofen, Germany. Measure at L band, but the GLR SAR sensor a long time ago. These are the buildings of the GLR. This is the S band. This is an autobahn, motorway close to Munich. This is an urban area, and here you have the airport runway, which has a very low reflectivity. Very low reflectivity means that this part here, the intensity is very low. It is so low that it becomes comparable to the variance of the noise of the sensor. Okay? And in this case, you see that, look, this is the modulus of the coherence, and it is close to 0 in this case. So if you want to detect the SNR decorrelation, a good way to do it is to make a plot. On one axis you have intensity, and on the other axis you have coherence. And when you have low intensity and low coherence, it is very likely that that these points are affected by SNR decorrelation. Okay? Because when you have you can have also a low coherence, but with a high intensity, and this is something completely different. Okay? This is due, in fact, this here is a good example of volumetric decorrelation because we are looking at a forest. Okay? But here on this part of the scene, we are dealing with SNR decorrelation, and you should recognize it into a SAR image. Huh? I think Francesco will give you some example of this afternoon during the practical. You have another term which is called temporal decorrelation. The scene changes between the acquisition. Okay, so this is a coherence map still of the same scene. Okay, but seen in the other way. This is the forest. This is the airport runway, and these are agricultural fields measured 1 hour. Okay, we make one acquisition. We fly again 1 hour later with a small baseline, so the interferometric effect is very small, and you see that, okay, the forest decorrelates, you have a low coherence over forested areas, but the agricultural fields and the airport runway, they are well correlated, okay? You fly 3 months later with a 0 meter baseline, so at the same, with exactly the same track than the first acquisition, and you have this, you get these correlation maps, okay? Everything which is black correspond to a low correlation. So it means that the reflectivity or the response of the environment change. And this is very normal. These are agricultural fields, so the people were working in the fields, they are changing humidity, there can be wind, there can be a growing of the plants can be growing, and the speckle you get 3 months later has nothing to do with the one you got during the first acquisition. And we see that most of the scene, it has a very low correlation, excepted urban environments and buildings, because the reflectivity of the building doesn't change over time. Eh? There's nothing growing on the roofs. Another example of temporal decorrelation with sensors that were running last century, during the 90s, ERS, they were the first one used to perform spaceborne SAR interferometry, and there were 2 of them. Okay, there was ERS1 and ERS2, and they had this temporal baseline of when they were working in tandem mode of 1 day. So you had an acquisition by ERS1 1 day, and the day after ERS2 was coming. Okay, and so this is always, I think it's Mount Etna in Italy. Yes, Mount Etna in Italy, and this is the correlation map you get. These sensors were working at operating at C-band, okay, and you see a very nice coherence map over most of the scene, particularly close to the top, because you have a mineral environment, no vegetation. In this case, there is no source of decorrelation, and you have the same first image of ERS1 and another one taken 70 days later, when ERS1 revisited the environment, the same scene, and you see that the correlation map, okay, changed a lot in the valley, okay, but also on the top of the mountain. And do you know why? Do you have an idea why? Due to maybe one eruption. This was not an eruption, but there was snow, okay. It has been snowing between the 2 acquisition dates, and snow has a slight response at C-band, but enough to change the spectral properties, and then it decorrelates. So when you have these kind of correlation maps, you need to be very careful when you perform interferometry, because of course the phase variance over most of the scene would be very high. Another source of decorrelation, I don't go into the detail. This is called range decorrelation. I normally don't present it, but since you will deal with biomass images, I need to present it. This is called range decorrelation or spectral shift. Okay, let me explain you the picture. This is a spectral domain, the vertical spectrum. So you take your environment and you apply 2D Fourier transform in elevation and in ground coordinates. And the SAR acquisition in this domain is comparable to a selection. You are selecting the spectrum of the environment over a bandwidth which corresponds to the bandwidth covered by the pulse you transmit. Okay. So you are selecting the width here corresponds to the bandwidth of your signal, and the location corresponds to the incidence angle you are using when you perform the first and the second acquisition. Okay? So this is called the Fourier slice theorem, something some people know. Okay? So you are selecting spectral bandwidth, spectral slabs over a specific spectral domain. And when you do this, you are sampling the response of your environment over the ky axis over slightly shifted domains. Okay? And when you look at, when you observe a natural environment, which is affected by speckle, if you apply a Fourier transform to speckle, it is still speckle, it is still not correlated. This means that you are selecting parts of the reflectivity of the environment that are not correlated. Okay? You see that this red slab here, when you project it onto this axis, selects only this part of the spectrum, and the blue one, the first acquisition, selects the second one. Okay? And they are slightly shifted. And the amount of shifting depends on the difference between theta 1 and theta 2, so the baseline. Okay? And it also depends on the width of the slabs you select into the spectral domain. And this width is the range resolution, okay, more or less. If you have a very good range resolution, in this direction, the W will be very, very big, and you see that the part that correspond to that are not common to image 1 and image 2 will be very small. But if W corresponds to very small values, then this part will be larger than the green one. Okay? The green one corresponds to the really correlated part in the spectrum, and the red and blue ones correspond to the ones that are not correlated at all. And the amount, the correlation, this effect, in fact, selecting parts of the spectrum that are not correlated creates a loss of coherence, which is a linear function of the baseline you are using. For a given configuration, a given resolution, a small baseline will lead to a lack of decorrelation, when a large baseline will lead to a complete, can lead to a complete decorrelation. I will illustrate this with a drawing. This is a classical configuration. You have your first acquisition represented here in blue, the second in red. The common part is the one represented in green, okay? And the uncorrelated part corresponds to the red and blue spectra here. There is one way to compensate for this effect. You just need to realign the spectra and to select the common part. And this way you eliminated the blue and red parts, which were not corresponding to the same ground spectrum domain. So this is an example of a coherence computed using raw interferograms, so without compensating the flat Earth. After compensating the flat Earth, and you see, so this is an airborne image, okay? For a given pair of tracks, the orthogonal baseline is much bigger in near range than in far range. When you go to far range, the interferometric effect becomes negligible, and you see that you have this change of correlation. Here, the correlation is very severe, and it becomes milder and milder as we go in near range. So the acquisition was performed on the left-hand side of the image. Okay? So this is in agreement with what was written here. This decorrelation is a function of the orthogonal baseline, which changes with the incidence angle. Okay? So this is what you get after flattening your phase, and after selecting only the common band, applying this kind of technique here, this is what you can recover the reasonable, the true coherence value, which is not affected by this range decorrelation effect. What do we lose? Remember, when we gain something, we lose on the other side. What do we lose? Something. We lose here resolution, because we had a bandwidth which gave us a resolution, I don't know, of 10 meters. And when we select only part of the bandwidth, then we lose resolution, which can grow to 15 meters or 20 meters. It depends on the value of this common band. Okay? But this is something most people are ready to lose. You are ready to lose resolution if you gain quality in the interferometric processing. Of course, this effect is even more pronounced when the true baseline that separates the acquisition increases. And you can reach a baseline for which the common part here is equal to 0. So it means that you have the green part here becomes so thin and the spectra are separated. In this case, there is nothing you can do because what you acquire on one acquisition and the other are not correlated, and there's no way you can compensate for this. And this is called the critical point, critical baseline, and you see it in this. Here you could compensate the decorrelation, but before on the left-hand side here, because the incidence angle is so steep, the baseline is too big, and there is no way you can recover it. I mentioned this, which I know this principle is quite complex, but you might be affected by this effect in the case of biomass, because the range resolution is really coarse. Do you know the value of the range resolution of biomass? It's 25 meters. In slant range. So in the ground range is 50 meters, so this is coarse. And the bandwidth is only 6 megahertz. And in this case, okay, this effect is very pronounced when the value here of W, the bandwidth, is very short. So in some cases, in the presence of topography, you may have a decorrelation in the biomass data that are due to this effect. The last point, and this is what we are going to study next, this is volume decorrelation. This is what you want to observe when you use interferometry to analyze forest, to characterize forest. Okay. Without going into the details, this decorrelation here is a function of the distribution of reflectivity in the vertical direction. Okay. It is given by a kind of Fourier transform-like expression. Okay. The correlation is more or less the Fourier transform of the density of reflectivity in elevation. So if you have some good a priori on this shape, okay, you can try to retrieve some characteristics of this f of z here, of this density of reflectivity by performing SAR interferometry. We'll see in 10 minutes that using only one acquisition is very risky. I mean, you need to use huge assumptions. In practice, what we do, we perform several acquisitions for different values of kz, and then we apply something which is like a Fourier transform to retrieve f of z. Okay, we try to invert this relationship. And this is called tomography. Okay. So interferometry and tomography are very, very similar. Just to give you a flavor of what we are going to do, let's say that you are measuring a volume, okay, a homogeneous volume of a forest which does not attenuate the signal and flies in the air. So it's a very unrealistic forest. Huh? But if you do this, then the density of reflectivity for this will be a rectangle, and then the coherence you will measure is a Fourier transform of a rectangle, which is a sinc, a cardinal sign. Okay, and because here you have f of z, which is a rectangle, so if you compute this integral here, you get something which is a sinc. So you will have, only by measuring the modulus of the coherence, you will get an idea of the width of the volume. This may sound really childish, really very simple, but this model is actually used. You will see Matteo, he will present Pauline SAR. Pauline SAR relies more or less on this. Okay? They use the sinc shape to get an idea of the height of the forest using SAR interferometry. So this, in practice, it works quite well. So illustration of volume decorrelation. Here you see a correlation map measured always over still over the DLR after a temporal baseline of 20 minutes. So in this case, at L band, there was no temporal decorrelation. And with a baseline of, 1 hour temporal baseline, and baseline of 20 meters. You see that all this environment here corresponds to agricultural fields, runway. This is a surface, okay? And surface do not decorrelate. There is no volume, okay? But over the forest, you have a decorrelation pattern that are very interesting. They are, I don't know if, yes, very, very interesting. This intensity, this part of the forest can be observed here. And what I like here is that these forests, they look very homogeneous from the reflectivity point of view. If you look at the intensity, that sounds like they are very uniform. When you look at the correlation pattern, you see that they are not uniform at all. Okay? Inside, there might be places where you have a low or high density, which they correlate more or less. The vertical structure can be different. So these two measurements, reflectivity and correlation, give you two different views of the same volumetric environment. And they can be used, they can be combined to retrieve some geophysical parameters of the forest. Okay? So if you want, we can move to the multi-baseline part of this course, which concentrates only, I don't know if I gave you the right one. Okay, the first page is wrong, but no problems. I will have to change I will send you the right file.
This is the correct
Yeah, the content is good, but the first page is wrong. So we are going to move from INSAR to multi-baseline INSAR and TOMO-SAR and concentrate only on this characterization of the last decorrelation term, the volumetric one. This is the objective of SAR tomography when you want to characterize forest. So SAR tomography, you may know the techniques. Okay, it tries to tomo means a cut, so you try to make to analyze to create cuts in an object by using a projection of some acquisition. You are measuring this object from different positions, and from all this acquisition, the objective is to retrieve some properties of the object in 2 or 3Ds, depending on the configuration of acquisition. If you go on the internet and you find there is a very nice book called Computerized Tomography, and what they do, they don't do the same tomography than the one we do. We concentrate on diffraction tomography. For us, waves are scattered, they are reflected, and they have a phase. Okay. Most of the application of tomography only are based, on most of the time on wave attenuation. Okay, they transmit wave and they measure attenuation, and from the attenuation, from different orientation, they want to reconstruct the tissues or the body that was imaged. We don't do exactly the same. We use diffraction tomography. This is a coherent processing, and of course, if you want to understand what's going on, you need to know what SAR interferometry is, which is your case now. Okay. The objective of SAR tomography or multi-baseline INSAR is to reconstruct the reflectivity of an environment in 3D using several acquisitions. What we want to do is very simple. We want to generalize. We are frustrated because SAR interferometry is limited. You need to make a large number of assumptions in order to characterize an environment, and we combine several interferometric acquisitions in order to overcome these limitations, okay? To widen the perspective of a characterization. So to do this, we use several acquisitions, okay, several interferometric acquisitions, and we will have a baseline diversity, spatial diversity, and using this spatial diversity, what you saw with Stefano yesterday, you can reconstruct the environment in 3D. For instance, I give you here this example that we computed in 2010, so more than 15 years ago. Really by taking the data processed by our colleague from Onera in France and applying the formulas from the book. Okay, we didn't try to understand much. We just programmed them, and we got this interesting result. This is the tomogram computed along a profile of a tropical forest in French Guiana. Okay, a very dense one. The trees are 30 meters high, and these measurements were performed at P-band. And over this profile, when you look at the distribution of the energy in elevation, you get this response, which fits very well with the LiDAR. Okay, the black lines correspond to the LiDAR, and of course the color here tells you if this is a high reflectivity or low reflectivity. And you see that over this forest, most of the reflectivity comes from the bottom interface between the forest and the ground, and the top one at the air tree interface. We understand what's going on inside the canopy of forest, okay, because we have scattering, but at the bottom, what we get is response from the ground, but this one is known to be at P-band not so strong, but most of the time we have a double bounce effect, okay, which is highly energetic. So the waves is reflected on the ground, bounces on the trunk of the trees, and goes back to the radar, and this creates all this reflectivity of this surface here, which can be observed very well with tomography. And with these measurements, we were able to reconstruct the surface below the canopy, and of course the surface at the treetop, and which compared to the LiDAR is not provide reasonable estimates. Okay. So SAR tomography is highly performing tool to characterize forested environment, provided that you are using the right frequency. You need to use waves that penetrate inside the forest. And this is why the biomass mission is flying. So to do this, to understand this tomogram, or to motivate the processing we did, you need to keep in mind the expression of volume decorrelation we just saw in the last set of slides, okay, which tells you that the normalized correlation coefficient, the coherence, is a function of the density of reflectivity in the vertical direction, and the relationship between these two is a Fourier transform, okay, like a relationship which is the integral and this exponential, this complex exponential term, and that by changing the baseline, okay, if you change the baseline, you change the spectral location, or you change the kz value at which you are computing this integral, okay? And if you combine, and if you use several baselines, then you will get several values. If you apply an inverse Fourier transform, you will get an estimate of this f of z. Of course, the quality of the estimate will depend on the number of baselines you can use and how they are distributed in the baseline space. Okay. But basically, if you understood this, if you understand this, you understood tomography. This is nothing but a Fourier relationship between your observation space and the space where you want to reconstruct the information. And just one thing here, when you look at this relationship, you understand that multi-baseline INSAR and TomoSAR represent exactly the same thing, just a different point of view. My friend Papatanasiou really likes to think that multi-baseline INSAR has several interferometric SAR responses because it is his background. I prefer to see multi-baseline INSAR as TomoSAR because this is my vision that better fits my background. But we are looking exactly at the same thing, okay? Sometimes it's more convenient to give an interpretation in one domain or the other, but at the end, you can always translate one property from one domain to the other. How do we consider forest? Forest is we simplify. I don't know if many of you are specialized in electromagnetic modeling, but this is we really simplify all these models because we adapt to the level of descriptivity of a SAR acquisition. This is the response you can get from a forest, or you can model from a forest if you use radiative transfer at order 1. It is too complex for us. We simplify this response by considering only the response from the volume, response from the top, and response from the bottom. Okay, and this is even this is even too complex. In fact, we don't, forest being a low density medium, we don't have this refraction effect, okay, this change of direction, because the density is not big enough. You would have this change of direction in ice or snow, because they are dense. Okay. In forest, the density is too low, so we still consider that the propagation host medium is air, and we don't have refraction. So you have reflection from the volume and from the ground. Okay. So we have two components. one corresponding to the ground, which is indicated here. We consider the ground as a medium you cannot penetrate in. So the reflectivity of the medium is non-zero, is zero when you are above or below the ground, okay? So you represent ground reflection by a Dirac, and the volume depends on your assumptions, and it depends on the forest, the frequency you are using to perform the acquisitions. Let's use of course, I know that we only have a few minutes to talk about this aspect, so I will not detail the calculation, just show you the major conclusions, okay, of this study. This is how you can model the response of a ground using a Dirac, okay? If you just inject the Dirac expression inside this integral, you get something like, at the end, the volume coherence of a ground, of a surface, is just an exponential, okay? So this shows you that interferometry is very well adapted to the characterization of surfaces, okay? When you have no volume, interferometry is enough, because from the interferometric phase, you can retrieve the elevation of the ground, okay, directly. When you have a volume, this is another story. Let's say that you have a volume, but a particular one which flies in the air and there is no ground below. Okay, you can simulate this when you do your own acquisition in an anechoic chamber. But in practice, this is not realistic. But let's take it as an exercise. You have a flying volume, and this is a non-attenuating volume. So it's scattered, but it does not attenuate the wave. In this case, the reflectivity is a rectangle, and the coherence here follows a cardinal sign, a sink shape. So it means that for a given baseline configuration, and you have a correlation whose value decrease or changes with the height of the volume, the width of the volume. So it's very interesting. It's a way to measure, in fact, one geometrical characteristic of your environment. You can measure the width of a forest by using this model. Okay, and the phase here gives you the mean elevation of the volume. Great. So you can localize, you can guess the width, and you can guess the position of the volume. This would be perfect if you had a non-attenuating media, but in general, of course, the wave is attenuated when it propagates through the forest, and in this case, you don't have anymore a rectangular shape, but you have an exponential shape whose Fourier transform is a bit more complex than the one I showed before. Without getting into the details, you get something, a coherence features that are maybe represented as this. When the extension in the medium goes to zero, you get back to the sink, to the cardinal side feature we had before. And with the extension increases, you have a kind of modification of this shape, which becomes flatter and flatter and flatter. Okay? And at the end, when you have a very strong attenuation inside the medium, the characteristic is completely flat. It means you have no decorrelation. And this is something you can understand. When you have a strong attenuation inside the medium, the waves do not penetrate, and this behaves as a surface. And surface, the correlation is equal to 1. So the physics are respected. And what about the phase? Okay, the phase, you have a variation of the coherence argument, which represent the interferometric phase from the behavior of a non-attenuating volume to the one of a surface located at the upper interface. And in practice, of course, you have a medium which may have a given extension, but you also have a response from the ground. If you remember well the tomogram I showed before, you have responses from the ground. And in this case, the expression is a bit more complex. You have a compound expression for the coherence, one part which corresponds to the volume, and one part which corresponds to the ground. Okay? And the balance between these two parts is given by the ground to volume intensity ratio, which gives you the ratio of these two, the intensity of the ground response and the one of the volume. And depending on this ground to volume intensity ratio, you may have one part dominating or the other. Okay? And retrieving the parameters of the forest using this formula is extremely difficult because you need to make a large number of assumptions or to use prior knowledge on the forest, call it the way you like, to set all these parameters, saying the ground to volume ratio should have these values, and then you need to fix some parameters to estimate the others. Okay. One way to overcome this problem is to use polarization diversity, but since you haven't done yet the course on polarization, I will not talk about this. I will jump a few slides. Okay. But basically, you use polarization, sensitivity of reflection to polarization to put yourself in configuration where the ground dominates or where the volume dominates. This is more or less the philosophy of this approach. Okay. But if you don't use polarization diversity, you can use baseline diversity, not only 2 acquisitions, but you can use 3, 4, 5, 10, 20. Okay, depends on how rich you are and how people are willing to pay for your acquisition. Okay. Do you know the number of acquisitions that biomass is using to perform SAR tomography? It's 7. Okay, 7 acquisitions, so it represents a large stack. Okay, and with these 7 acquisitions, we are going to sample, okay, the spectral domain at 7 positions here. And from these 7 points, applying Fourier transform, we'll try to retrieve the reflectivity, the shape of the density of reflectivity in elevation. This is as simple as that. You can also represent this sampling using on this model. This is the correlation model corresponding to a volume with a varying attenuation. And you see that if I measure the correlation for different KZ values, then I will be able to reconstruct, to select which one of this profile is the best one. Okay? Really explain well my data. And I will conclude on this analysis here. These are tomograms performed, I think it's on, I'm sure it's on a boreal forest at L-band in a forest located in Sweden, measured in the frame of the BioSAR2 campaign sponsored by ESA. This is a profile here, where you have no forest, and again no forest at the end. And these tomograms were performed at 3 polarization. Don't look at the polarization. Maybe we can concentrate only on the HH1. This is the result of tomography, which shows you the distribution of energy in the vertical direction. Okay, and here I just played a game. I computed the interferometric phase center, so I just computed the interferometric phase, compensated for the terrain, okay, so that I get no fringes, okay, and I just translated this phase into elevation, and now you know why. How? I took the phase divided by kz, and I got the height, okay, and here you have the location of the phase center inside the forest for different pairs of images, the first image and the second, the first image and the third, fourth, fifth, and sixth. Okay? And these images have been sorted so that they have an increasing baseline. Okay? And so it means that here the baseline is small, it becomes bigger, 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 and huge at the end. And what do we see on this picture without getting too much into the details? I can see that here I have a phase center which is close to the top of my forest, at least to the top of the tomogram. And here it is close to the bottom of the tomogram. Okay, so here and you see that this effect can be observed as the baseline increases here. I have the phase center which is progressively projected onto the ground. Why this? Why this? If you get back a few slides and you look at this model, you know, when the KZ increases, the volume decorrelation goes to 0. Okay? The volume correlation goes to 0, and what remains is only if the volume correlation goes to 0, you get only the ground correlation 1. So you can, it is a way to isolate this term. Okay? Increasing the baselines gives you less contribution from the volume and more from the ground. And this is observed when you change the baseline. This is, by the way, I didn't tell you, this is near range and this is far range. So for a given configuration, in near range, the incidence angle is smaller, So the orthogonal baseline is larger, and it becomes smaller and smaller and smaller as the incidence angle increases. And you see this effect. Let's say you consider this profile. Here, the phase center is exactly on the ground, and then it goes up into the canopy. Gianfrancesco. It goes up into the canopy because the baseline becomes, the orthogonal baseline becomes smaller. Okay? So here you have a nice illustration, or at least something you can understand, of how volume and ground correlation contribute to the total interferometric pattern. Okay? And of course, when you perform SAR tomography, when you perform this simple inverse Fourier transform, you are just using at the same time all these combinations to recreate the vertical distribution of intensity. So this is very powerful. Okay? Let's see what I can say in 1 minute. Okay, nothing. And okay, I will maybe conclude on images. Okay, some applications of SAR tomography. One of the most impressive I know has been done by Stefano, you saw yesterday, over this glacier in the French Alps. No, in the Alps, sorry. I think it's Austrian Alps, at Elband. The glacier is a dry one, it's a dry glacier, so the waves are penetrating, there's no liquid water. And they were flying with a meta-sensing airplane, a small airplane, and they were describing loops over the glacier, 20 loops, and after very intensive signal processing, Stefano was able to recreate a 3D cube of the glacier, and here you see some examples of polarimetric maps recreated at different elevation below the glacier interface. Okay, and you see that the structure changes at the beginning. Close to the interface, you have a given texture, and this changes a lot. You see cracks when you go down into the glacier. Something about forests. These are results computed over this BioSAR2 data set acquired in Sweden at Elband also. So this is a reflectivity map. On the left-hand side, you have the forest height measured by a LiDAR, and this is the digital elevation model. You see that there is a gentle topography over the scene. And this is what we do this afternoon. With tomography, you can reconstruct this reflectivity map at different elevation. And here you see that over this scene, this part corresponds to an area without trees, where the intensity is maximum when you are close to the ground, and when you go up, you have this. You can analyze the structure of the forest, and here you see that the reflectivity is maximum at 10 or 20 meters above the ground, because this is a rather short forest. Of course, this application of the Parakou test site, French Guiana, the one I mentioned before, really we were very surprised to see by only using data applying a spectral estimate Fourier transform, we could get such nice results over this tropical forest. In urban scenarios, you can also apply tomography to reconstruct buildings, and these are buildings you constructed with only 3 images. So this is the minimum configuration to do tomography or multi-baseline in SAR. And you need to have one short baseline, one large baseline, and you combine to have spectral diversity. And then the results can be compared with LiDAR. To be honest, I would say that I consider tomography much more useful to characterize forest than to characterize urban environments, because in this case, many urban or many big cities have already been mapped using LiDAR, which is really a tool that is well adapted to this kind of environment. Okay. For forest, this is not always the case. Just for your information, you can show in French Guiana, but on many sites, that when you look at LiDAR maps for the ground, when you compute the shape, when you compute the slopes of this LiDAR map, they look very too simple, in fact, because there are very few points that actually go to the ground. Okay, they interpolate these points, and at the end you get slopes that are not realistic. And this is why we believe that the DTM we are trying to process using the result from the biomass mission will be useful, as it will give a natural, to recreate a natural slope of DTMs below the forest. And I will stop here. The rest you can read, or if you have questions, don't hesitate to send me emails. If you want some bibliography about all what I told, don't hesitate to ask me, and I will be happy to help you.
We have actually 10 minutes if you would like to.
Yes, okay. I have 10 minutes. Good, perfect. Good surprise, at least for me. Sorry. Okay. Just now, this was okay. I was not prepared to get this 10 minutes free. Okay, maybe a comparison of interferometry and tomography in 2 minutes. Okay, how would you estimate the phase of an interferogram when you do interferometry? Of course, what you do, you compute, you take the first image. Okay, you take one image, you multiply by the complex conjugate of the other one, you take the argument, and you get the phase difference. Okay, this is how you do. If you do tomography, you don't do it exactly this way. What you do, you take the two acquisitions, S1, S2, you take a linear combination of these two, and the combination implies a phase term, phi, okay? And when you do this, you create a function, and you look for the maximum of this function, okay? And this function reaches a maximum when the argument is exactly equal to the phase difference. So if you have only two images, retrieving the phase using this technique takes 1 second. This one, you need to do a small program to do it, so this is not very efficient, okay? So why am I presenting you this? Because in the multi-baseline case, if you want to perform the analysis in the interferometric way, then this is extremely difficult. You have M acquisitions, you have many combinations. You can take the first image with the second with the fourth, and you looking at all these phases simultaneously is, mission impossible, okay? So if you want to really analyze what's the content of the data, then if you resort to this tomographic way of converting phase difference into amplitude, okay, as I said before, then, and this is in fact what you are doing is a Fourier transform. If you apply a Fourier transform to your data, then suddenly you will refocus the responses of the scatterers you have been imaging at their correct location in elevation, okay? So this is really very powerful. When you have only two images, there's no gain, of course, or even you lose time. But when you have more than two images, then it becomes almost compulsory, okay? With 3 images, you can try to look at the phase difference between 1 and 2, 2 and 3. But when you have 7 images, like in the case of the biomass mission, no way you can do this. And the quality of the reconstruction depends, of course, on as always, on the resolution. And the resolution is provided by the baseline distribution, okay, the KZ distribution. I will jump into, okay, this is the representation of the baseline distribution. This, you have a set of KZ values, KZ2, KZ3, KZM, okay? And the resolution you have is given by the domain covered by all these KZ, okay? We call it delta KZ, and the spacing between two consecutive acquisitions is called dKZ. And therefore, a regular array, which is the case for biomass, when the baselines are only regularly they lie on a regular space. In this case, there is a clear relationship between the bandwidth and the spectral sampling. This is M, the number of images. Okay, and the resolution is given by. This is a very important relationship. The resolution is given by 2 pi divided by delta k. Okay. So with the baseline now, if I give you the configuration of biomass, you can already compute the vertical resolution of biomass like this. And you know the orthogonal baseline, you know the range distance, you know the wavelength, you know the incidence angle. You get to the KZ, okay? And from the KZ, you look at the minimum KZ, the maximum KZ, you make the difference. You divide 2 pi by this, and you get the resolution. In the case of biomass, in the tomographic phase, it will be around 27, 30 meters, okay? And using the relationship I mentioned before, this you can compute the ambiguous height, which is exactly the one we observe in the interferometry case. This is the height at which your tomogram will repeat when you apply your Fourier transform, okay? So you will have a resolution which represents the width of this main lobe here when we reconstruct the response of a target, and the ambiguity is the distance which separates 2 consecutive peaks when you reconstruct your tomogram. Okay? And the relationship between them is a factor, is m, the number of images. So in the case of biomass, it will be 7. Okay? So if you have a resolution of around 30 meters, you will have an ambiguity of around something like 200 meters. And when you design a tomographic experiment, and I will conclude on this, there are some rules you need to follow. You need, of course, to select, to tell the pilot, or to select the orbits which correspond to a given resolution, okay, and a given ambiguous height. So if you, let's say that you are dealing with a configuration with you have 6 images, okay, and you use a given baseline which gives you this vertical resolution. If you divide the baseline, the spacing between 2 consecutive images by 2, you will not change, you will, of course, change the resolution. And for a fixed number of images, you will also change the ambiguous elevation, okay? So you will lose resolution, but you will gain because you will be able to observe larger or taller forest. If you keep the same spacing, same baseline sampling, and you increase the number of images, you will not change the ambiguity, but you will change the resolution. So you'll be able to discriminate smaller details, okay? And of course, if you use more images and a smaller sampling interval, then of course you will have a non-changed resolution, but you will improve your height ambiguity. So how do we do in practice? In practice, using what you don't want to have when you do tomography is to have an ambiguous response. Otherwise, because in this case you will have the tomogram that are superimposed, and you cannot analyze this kind of results. So the rule of thumb is to select the ambiguous height to 2 or 3 times the maximum height you expect to see in your scene. Let's say you are observing trees that will be 40 meters high. So you select your ambiguous height, you set it to 80 or 110, something which is much larger than the actual tree height. And after, you need to select m, the number of images, so that you have a reasonable resolution to analyze the forest. Okay, so it depends a little bit on the compromise you want to set between ambiguity and resolution. In this case, if you want to have an ambiguous height which is twice the maximum elevation in your scene and resolution, if you want to have 3 resolution cells within your forest, then you end up with a number of images equal to 6. Okay. And this concludes this part on the multi-baseline SAR interferometry. We'll have a break, and I will find you. We'll start again after. I will make a very short introduction to polarimetry before giving the floor to Alberto. Thank you.